Swayam Prabha. Digital India. Educated India.
So in today's class, we will discuss particle size distribution. Information on particle size is very important in dispersed multiphase flows because it dictates the particle dynamics, as you have seen in the previous class. For example, the Stokes number, it is sensitive to the particle size because it depends on square of particle size. So that is why the knowledge of particle size is important, and we need an appropriate way to present the particle size distribution. Okay, so here we will consider one example from droplet sizing data measured from a spray. So imagine you have a measurement tool, let's say a laser diagnostic, and you could measure the droplet size in a spray. So you have a small probe volume and you can identify one droplet at a time. So one droplet comes into the probe volume, you identify that, you measure its size, then next one, and it goes on. So you have a measurement data, something like this. So for example, the first measurement gives you size around say 25 micron, the next one 30 micron, and so on. Now if you look at this plot, we can hardly infer anything, any useful information from this. At most you can understand that the particle size ranges between, let's say, 20 micron to say 90 micron. But if I ask you how many particles we have, or do we have more particles between say 20 and 40 micron compared to 60 and 80 micron, it's difficult to understand from this. So how should we present the droplet size data in this case? So we need to divide the particle size range into number of bins by selecting an appropriate bin size, let's say that is delta D. Then we divide this distribution into multiple bins, something similar to this. So then we count the number of particles in each bin. So for instance, let's consider this bin which starts say from about 60 micron to about 68 micron or so. So in this case we know the limit, and the center of this bin is represented by Di. Then we count the number of particles, and that is Ni. Now we go on doing this for all the bins. For example, let's say for this bin you count the number of particles, in this case say 1, 2, 3, 4, 5, 6, 7, 8. So you note this number. So Ni for this bin is 8, and what is Di here? That is the center of this bin, the particle size at the center of this bin. Once we do this, we can calculate the probability or number frequency by taking the ratio of the number of particles in one bin to the total number of particles. So this gives us the probability or number frequency. So let's see what do we get if we do this to this existing data. So we get a plot like this. So here basically we have shown the number count Ni for each Di. Okay. So you see the numbers. For example, the first one is around say 2000, second one around 4000, and so on. But we know that this number count corresponds to a bin rather than a particular size. This size is basically representative of that bin. So we can show it this way also. Okay, so this is a histogram of the particle size distribution. And then so we know the number here and we divide this with the total number, and then we get the probability as I mentioned earlier, and we get a distribution like this. Okay, so why do we need to calculate the probability? What is the problem if we just keep the number count here? So in that case, comparison between different cases will be difficult. Why? Because this number count depends on the total number of data that we measure. Let's say in one experiment you measure 10,000 number of droplets. In the second experiment you measure 20,000. Then obviously these numbers will be higher for the second case. So how do we compare? So that is why we normalize the number with the total number. So this is how we get the probability distribution. But then an interesting question appears. So now I can do this for different bin sizes. So for example, I had taken the bin size, the data that I had just shown, I mean this one, here I have 4 micron bin size, here 8 micron, here 40 micron. Now the question is, what is an ideal bin size then? So how do you select a bin size? So the bin size should be selected such that we have large number of particles in a bin, which ensures reasonably smooth distribution. So what is meant by smooth distribution is that that indicates an appropriate trend. For example, see, look at this. So if I just join the center points here, this will give me a distribution like this, and this tells me that larger number of larger the particle size, smaller is the probability. Okay, but now look at, let's say, this. What can we argue here? Can we say that the probability of this bin is less than this? The answer is most probably no, because of the uncertainty in the data. Because here we have fewer number. So close comparison like this is not possible. Okay, so we need large number of particles to ensure this kind of smooth distribution. But what happens if you choose a very large bin size, let's say like this? Then in that case, we lose important features like multimodality. What is meant by multimodality? This means that the behavior of the particles within that bin, for example, you see between 20 to 60 micron here, or say here, we see some trends which are completely absent here. Okay, so that kind of limits the large value of bin size that you can select. Then if we use, on the other hand, too small bins, then the data becomes noisy and we have poor probability estimation. So if you go on reducing the bin size, also we have a problem. And moreover, the bin size should always be larger than the measurement accuracy. So if the accuracy of measuring droplet size in this example, let's say, is 4 micron itself, then there is no point in having a bin size which is 4 micron or below that. It makes no sense. In fact, it should be at least 2 to 3 times greater. Then only it makes sense. So you see that the bin size is selected as a trade-off between these two factors. Okay, And the ideal bin size depends on the particular application that you are interested in. So let's say you have some applications where you are really concerned about small change in particle size, because let's say small change in size changes Stokes number and the behavior of the particle, and in that application that kind of sensitivity is required. Then you have to select the bin size appropriately. If you select something like this, it won't work. Okay, so it depends on what you are interested in. There is another method also to represent particle size distribution, and that is by considering cumulative distribution. Cumulative distribution can be expressed, or cumulative probability can be expressed through this expression. So physically, what does it mean first of all? Okay, this means the fraction of particles with size less than or equal to some size. In this case, let's say dk. So let's say dk is the size for which you want to find the cumulative probability. This means that you are referring to the fraction of particles which are less than this size dk in this entire distribution. So how do we get it? By adding up the probabilities below that size. So this mathematical expression basically tells you that. Okay, so for instance, if I say for this size dk, the cumulative probability is 0.5. If you get a value of 0.5, this means that 50% of the total number of particles are below this size dk. Okay, so what will be the cumulative probability of the maximum size? Whatever maximum size you have, what will be its value? It has to be 1, right, by definition. So here you can see the comparison between the probability distribution and cumulative probability distribution. Okay, so the cumulative probability distribution, by definition, it will always increase, but you see that the slope becomes smaller and smaller. Why? Why you see that the slope is smaller for larger particle size? Maximum has to be 1, but why the slope now reduces? So you see that from here to here the slope reduced significantly, and from here it does not change much. Why? Because you have smaller number of larger particles. So you have very few particles here beyond say 70. Okay, so their probability is less than 1% even. So that is why this does not change. Okay, so now we can look at different particle sizes that corresponds to different values of this cumulative fraction. For example, this. So as I said here, the particle size 30 refers to that size below which almost 50% of the total number of particles exists, and this size, which is around, let's say, 65 micron, this represents the size below which nearly 95% of the particles exist. Okay, so this is basically another way of presenting the particle distribution. Next, we will see mass probability distribution. So till now we are considering, or we are calculating the probability by considering the number of particles, but we can also consider the mass of particles. What does it mean? So this is a way to describe how the liquid mass is distributed across the particle size rather than only the number. So why this is important? Because larger particles carry more mass. Why? Because the mass is proportional to d cube of the particle size. So imagine you are injecting, let's say, some fuel spray into your combustion chamber. So you have large number of small particles, few large particles, but you find that the large particles carry, let's say, 50% of your total mass. Then this means that your atomization is not appropriate. So we can't be happy only with the number of the particles. We have to, so depending on the application, we have to consider the mass also. So that is the reason why mass probability distribution is important. Yeah. So this is expressed by this expression. So if you remember, the number probability, we didn't have these terms. So now we have this. What does this indicate? So this indicates the volume basically. So you consider each bin, okay, and for that bin you calculate the number of particles, and you assume that all particles in that bin are of size this di, and you calculate the volume of that particle. What is that? Pi di cube by 6, and you do the same for all bins and you sum them up. So finally the pi by 6 term cancels out, and what you get is this. So what do you think now? How the distribution would change? Instead of number, now I will plot the mass probability. Let's see. So it looks like this. So this is the number probability and this is the mass probability. So what is the main difference? The peak has now shifted. Okay, the mass probability looks very different, and it indicates that you have more mass contained in the larger droplets, but still you have this decreasing trend. Why? Because the number reduces also. So the volume corresponding to a bin depend on the number as well as on the particle size. Because the number reduces, so finally this also becomes very small. Okay. So now, similar to cumulative number probability, we can also calculate cumulative mass probability. Okay, and the expression is basically same. And here you can see the comparison between cumulative number probability and cumulative mass probability. So what is the difference? This approaches one much quicker compared to this. Okay, this is because of contribution from the large droplets. So in this case, if you consider the same particle size, let's say 30 micron, so this represents 50% of, nearly 50% of the total number of particles which are less than 30 micron. But if you see the mass probability, it is much lower. I hope you could understand. So this tells you that below 30 micron, you have 50% of the total number of particles, but only 10% of the total mass. We'll see characteristic particle size. So now let's say you want to buy an injector for your application, whatever application you have, and you go to market, and then you have to specify what is your requirement, right? Now, if you say that I need an injector that gives me size between 20 micron to 110 micron, then it won't be convenient, right, for them to specify the injector. So usually we specify a characteristic size, a typical size that we want. For example, an average size. So if you just average all particle size, okay, and say that, okay, I want an injector with average size of 30 micron. Okay. So that is why we have to, means apart from the particle size distribution, information on the characteristic particle size is also important. But the problem is that just one characteristic size cannot represent the entire distribution. For example, average size. It cannot always represent the behavior of the spray. In this example. Okay. So now we can define characteristic particle size based on particle distribution, based on probability distribution of particle size or cumulative probability distribution of particle size. We will see this. First one, or first way to calculate the calculate a characteristic particle size is just the arithmetic mean diameter, or this is called AMD, and this is represented by D10. Why it is D10 you will see soon. And here what you do is that you just add up all particle size, divide by the total number of particles. Okay. So that is what is arithmetic mean diameter. But we can also define surface mean diameter. So what is surface mean diameter? It is given by sum of square of particle size divided by the total number and take its square root. This is called surface mean diameter. I am not writing it as SMD because I am reserving that symbol for another characteristic size, and this is given by D20. So similarly we can have volume mean diameter. So in this case we count the total volume in each bin and then you divide with the total number of particles and then you take cube root of this. So why are we doing this? So you imagine what is meant by characteristic particle size. We want a particle which is a representative of the entire particle size distribution. Okay. So now let's say you have one particle size like this, and let's say this is D30. Now if I assume that all particles are of same size, then its volume will be pi d cube by 6 and total volume is this. Okay. So this represents the total volume if I assume that all particles are of same size D30. Okay. Now this is essentially equal to okay. This is equal to this, and then I can write that okay, and then I get this expression. So similarly, surface mean diameter represents one particle size that is a representative of the surface area of all particles. Okay. So then we can define also Sauter mean diameter, which is given by this expression. So you can imagine this as the ratio of total volume of all particles to total surface of all particles. Okay. Now we can write a general expression for the particle size, and it is given by this. Okay. So, here you put m, appropriate values of m and n, you will get an expression as like this. See, for example, if you put m is equal to 3, n is equal to 2, here you get D32, which is the shorter mean diameter, and the expression is basically this. Okay. And you can easily check this for other sizes. Now, the question is, why do we need all this characteristic size? So, again, it depends on the application. For instance, if you are interested in spray combustion, let's say, there you want the fuel droplets to evaporate fast. Okay. And not only that, you want to atomize it such that the surface area is maximum for a given volume. So, you want to inject, let's say, 3 ml of liquid fuel, but you want to achieve high surface area. Okay. So, it is not only about the area, it is also about how much fuel you are injecting. What is the volume of fuel you are injecting? So, that is the reason why SMD is more important if vaporization is of interest. And in that case, what do you want SMD to be, higher or lower? You want to maximize area for a given volume. So, SMD should be lower. SMD should be smaller. Okay. But for that case, if you consider rather arithmetic mean diameter, then what will happen? So, a typical size distribution looks like this, particle size distribution. So, if you calculate the arithmetic mean diameter, more likely it will be close to the peak. It won't be at the peak value, but close to the peak, say somewhere here. But if you calculate SMD, it will be, let's say, somewhere here. Why? Why SMD would be larger than AMD? Because it is controlled by higher powers of particle size. So, then you can means you may predict the combustion behavior wrongly if you assume that your particles are small, because only because you considered arithmetic mean diameter. Okay. So, depending on applications, we have to select the appropriate characteristic particle size. Okay. Now, the second way is based on cumulative probability of particle size that I just discussed before. So, we can define a characteristic size, say D50, below which 50% of total number of particles exists. So, this is based on cumulative number probability. Similarly, I can have cumulative mass probability. I can bring in cumulative mass probability and say that D50 refers to the case where or refer to the size such that 50% of the total mass of particles is less than this size. Okay. So, here it need not be 50 only. So, it can be anything. So, for example, it can be D90. What is D90? D90 based on mass, cumulative mass probability is the size below which 90% of particle mass exists. Okay. So, in many applications, these are also used. Okay. Now, we will move on to theoretical particle size distribution. So, till now, our discussion revolved around discrete particle measurements discrete particle data obtained from measurements. Okay, so the probability distribution was discrete, means what? You define the probability for some specific sizes only. Okay, however, theoretical particle size distributions are also important. Let's see why it is so. So the theoretical size distribution basically refers to a mathematical function which represents this complex data set with the help of few parameters. So now let's say I want to compare the particle size distribution in two cases. Let's say I want to compare the size distribution in two injectors. Now, how do I mathematically compare? So I can compare, let's say, some characteristic size. Okay, but again, characteristic size is not, okay, it is a good representative of the size distribution, but it does not tell you everything. For example, it does not tell you about the spread of the distribution. You don't get any information about the spread. Okay, so if we can describe the measured particle size distribution through some mathematical functions, and where we can define some parameters which controls that function, then we can compare those parameters. For example, I can define something called a spread parameter and I compare. Okay, so that is why the mathematical functions are important. As I said, to compare different samples or processes using common parameters, and importantly, the engineering models that we use for either for theoretical analysis or for numerical simulation, that requires the particle size distribution as an input. It is a very, very important input to the numerical simulations, or if you want to do any theoretical analysis. So now, but before we understand that, now we have to also understand what is meant by probability density function. So till now we discussed what is probability, but now what is important is probability density function, because we are now going to prescribe a mathematical function which is continuous in nature. It is not discrete as in the case of measurements. Okay, so probability density function is nothing but the probability that we calculated divided by the bin size. But here we are considering the limit where the bin size approaches 0. So you imagine, just assume that you have large number of experimental data such that you can reduce the bin size, and even then you have enough number of particles. And imagine you go on reducing the bin size and make it 0. 0 means you have one value. So then what you obtain here through this ratio is called probability density function. So that is the difference. So it is not same as the probability. So if you know the probability density function, how can you calculate the probability? Just by integrating the same function. Okay. And how do we, so if we integrate the probability density function from 0 to the maximum value, we will get 1, because total probability is 1. So basically the local probability for a given size d is now given by this. Okay. Now, while probability itself is unitless, what is the unit of probability density function? Is it also unitless? The answer is no. In this case, its unit will be, let's say, micron inverse or meter inverse. Okay. And we can define now cumulative probability using the probability density function. So here if you see, again we are considering this probability for size d, and we are summing up all the probabilities from 0 to that value. So this is cumulative probability. So basically we can define all the parameters that we discussed for discrete function using continuous function. And as we expect, the cumulative probability for the maximum size is 1. So now what are the typical theoretical particle size distributions? So mostly two types are realized which show good fit to experimental data. So now this is also important, that there are many continuous functions, PDFs are available. Can we pick up any one? No, the answer is no. This has to fit with at least some experimental data. We may not have a theoretical particle size distribution that represents the size distribution in all multiphase flows. No, that is not practically possible. Okay, but at least for some flows. The first one is log normal distribution. For that we have to see first of all what is normal distribution. So I assume you are all aware of normal distribution. So which is given by this expression. Here mu is the mean and sigma is the standard deviation, and typically it looks like this. So it's a nice symmetric distribution. Okay, the question is, can particles size follow a normal distribution? Okay, the answer is unfortunately no. The real world particle size distributions are not symmetric. They are not Gaussian. Okay. Rather, they tend to be positively skewed. So what is meant by positively skewed? This means that you have a longer tail for the larger size, as we have just seen in the previous examples. And typically we have many small particles and few large particles. Now the question is, why is this so? Why it is not random? So for that purpose, let's consider one example. Let's say you have few people standing here and they are talking to each other. Okay, and then few more people joined them, and they all started talking randomly, and then more and more people went on joining this group. Now let's say you put some kind of a sensor that measures the sound intensity, and if you plot the sound intensity with respect to say this radius, you will get a nice Gaussian distribution, because it refers to additive random process. So you have a random process which is additive in nature. Okay. Now, why we don't have that in the case of real world multiphase flow applications? So I can give an example in the context of an atomization process. Okay. So that process refers to multiplicative random process. So what does that mean? Now let's say you have an atomizer, and first after the primary breakup zone you generate some set of droplets like this, ranging from small to large. But what happens? Some of the large droplets further break to produce small droplets. Okay. See, this process is quite complex. Okay. This is a very, very simple way of describing what I intend to. Okay. Don't think that this process actually is like this. It is very complex process. So Now these small droplets, they bursted into, these large droplets, they bursted into these small droplets. Okay, and now you have this population going up, and you have this, the population of the larger droplets smaller, because they don't survive somehow. Okay, so this refers to a multiplicative random process. So that is the reason why we don't have particle size distribution which follows normal distributions. But interestingly, this follows log normal distribution. Now, what is log normal distribution is that you don't have the size which follows normal distribution, but logarithm of particle size which follows normal distribution. Okay, so you can imagine something like this. You have a function like this. So you have the logarithm of this follows the normal distribution. Okay. Now this is expressed through this equation. So log normal distribution. So the difference here is that you see, instead of x, here you have ln d. So now ln d is the variable, not d. And here, but you have to remember that here mu and sigma are defined based on ln d, not d. Okay. So the distribution looks like this. The log normal distribution, first of all, it is defined only for positive value of d, which makes sense and fits well to the practical case. Okay, that we always have a positive value of the particle size. And then you see that it is positively skewed also. So, but interestingly again, this is the log normal distribution is suitable for number based particle size distribution, rather mass based. So if you remember, I had shown you the comparison between number based distribution and mass based distribution. For number based distribution, this holds true, right? So we can't say this in the context of mass. Okay, so for prescribing the number based distribution, log normal distribution works well. So now if you have an experimental data, how will you find this? What are the parameters which you need to define log normal distribution and check if it fits or not? So you need to, so you have the particle size, so you just take logarithm of that, find the mean and standard deviation of this parameter, and then plug in here in this equation. Then whatever value of d you give, it will give you the probability density function. Please remember, it is not probability. Okay, so the next distribution is called Rosen-Rummler distribution. So in this case, we have the cumulative form is expressed like this. This is the cumulative form, and there is a reason why we are starting with the cumulative form. Actually, when it was proposed, the cumulative form was only proposed. So what is meant by the cumulative form? So here we are considering the fraction of particles which are less than a particular size. Okay, so earlier time this was used to prescribe the particle size distribution for coal particles. So you get coal particles, then you have some sieves. Imagine you have some sieves, you put it, and then you collect particles below the size equal to the mesh size of that sieve. So whatever you collect, you measure its weight. Okay, you know the total weight, so you get the fraction. And now you use different sieves and you can get this distribution. So you see how by measuring the mass of the particles only, you can get this. So you can get basically the cumulative fraction. So once you know this, then we can find the probability density or mass fraction density, okay, by differentiating this. And so this, if you see, so this is the probability density function. So here you have two terms. What are those? D naught and N. D naught is known as characteristic size or scale parameter, while N is known as spread parameter. So here you have two parameters. One gives you the characteristic size, the other gives you the spread. Okay. So here, higher the value of N, this means you have narrower size. Narrower size distribution. Okay. Okay, here we are changing both the D and N. So now the question is, in this case, how do we calculate these scale parameters and the spread parameters if we have the experimental data? Okay, so that can be done through this interesting way. So you consider this cumulative form, take double logarithm. Okay, it is easier to show that this can be expressed as this. Okay, and then here you have basically a linear equation, and from that the slope of this line will give you the N, that is the spread parameter. While once you know the slope and you know this B, then you can calculate what is the scale parameter. Okay, so there are other distributions also which are used in some applications. For example, gamma distribution is also used, but mostly it is log normal and the Rosen-Ramland distribution. Okay, so we'll stop here. Thank you.